Okay, so last class we kind of reviewed everything we covered so far. What I'd like to see today is what do you guys remember from this review? You know, what was the first thing we covered in this class?
Last class.
Vectors, speed.
In the whole course, right? What is everything? What is the first thing you learn in the course?
Vectors,
Vectors, right? So what is a vector?
align with direction.
A line with direction? Is that how you would define it?
It's
Align, oh, yeah. Isn't it like a distance with direction?
Distance. Well, before that, in general, why we came up with this idea of vectors? Did you see vectors in other classes, or did you learn about vectors? Maybe in math, if you had math.
no, it's
Yeah.
a way to it's a way to measure things.
To indicate direction?
But do we need this in physics?
We do.
Yes.
Huh?
Yes, to measure distance, to measure forces, to measure velocity, to measure.
What are those things? Those are things that we measure, right,
Yeah.
in physics. Some of them looks like, force. What about temperature? Is temperature a vector?
No, it's a scalar.
No, it's not. So we're able to differentiate, physical quantities. Those are physical quantities, are things that we measure, right? Things that we measure. And some of these physical quantities that we want to describe the world, right, with maybe force or velocity, some of them requires a direction. Not only direction, but they have a magnitude, right? So 100 degrees is more than 50 degrees, right? That's a scalar, right? It doesn't matter. But if I'm driving at 100 meters per hour or 50 meters per hour, right? That's also a magnitude, to give an idea of, how fast I'm going. But also, beyond that, we need direction.
Yeah.
So that's why we learn about vectors and scalars right at the beginning. That was the first thing we did. We also learned about units, conversions, and all that. Very important when we describe, we make a measurement, it's very important to identify what unit are we using. Are we using meters? Are we using inches? Are we using feet? All that is important. Okay? So vectors, that was the first thing that we really covered. And then operation with vectors, right? How to add a vector, right? And how to, let's talk about product. You guys remember the product vectors? So if the vectors are on the same direction, like vector A and vector B, that is an easy thing to do, right? You just, if this is 3, this is 5, in terms of magnitude, I just add 3 plus 5 is 8. And I know the direction is the same there. But if the vectors are perpendicular or on an angle like this, right? Then we need to use a different way, right? To add them. We also talk about notation, right? Vector A can be a AI plus BJ, right? What is I? I is the unitary vector in the x direction, and J is the unitary vector on the y direction. You guys remember that, right? So then I can have a vector B here, and then I have CI and maybe DJ. And how do I add them? Well, I just add, A and C, B and D, right? If I want to add them. If I want to subtract, I just subtract them. Now, what about product of A times B? Now, when we talk about product of vectors, there are a couple of different products, right? We call one, there are 2 names. Where are they? Do you guys remember? The name
The dot product and the cross product?
Exactly, dot product, and then we have the cross product, right? Now, the dot product, the result is going to be what? Why we, first of all, why do we have two different products?
Didn't one have to do with the projection component?
The dot product, the result is a scalar. The cross product, the result is another vector. That's what it is, okay? So if I have now A, the module of A times the module of B, cosine the theta, the angle, and for the product is going to be A times B, and that's going to be the sine of theta, right? Now, here, this is a scalar. This here is another vector, okay? But what is the direction of that vector, right? Well, the direction of that vector is determined by what I call maybe the right-hand rule, okay? I have two vectors, and there is an angle here, right? So I use my hand just like that, and I put here like A times B. A times B, I do like this, my thumb is pointing outside, so this here is going to be going outside, okay? Now, if this is A times B, okay? So I'm going to have a vector C with pointing to outside. Now, if it's B times A, so now my B is here and the A is there, so I'm going this way and my thumb is pointing to inside. So that is now the vector, the result of the product B times A is going to be a vector going inside the board, okay? And that, remember we covered torque last time, right? Now, an example of a dot product would be work, right? We have, a distance, a certain distance, a displacement times the force. That's going to be work. That's a dot product, okay? So this is a distance times force is work. Remember, work only when you are able to, yeah.
How do we differentiate between both equations?
Which, this equation?
Yeah, that scalar and vector.
Yeah, the dot means the dot product, right?
Okay, yeah.
And this cross here, this X with a little circle here, we call that the cross product.
But in a real life example, how do we differentiate? Or if we're doing an example on the test?
Yeah, this is an example of a scalar, of a dot product that gives a scalar, right? Now let me give an example. What would be an example of a cross product that we just learned last class?
Opening the door.
Torque, right? Torque. Torque is the radius times the force, and that's going to be torque. Okay? So here I have my radius, and here I have the force. Okay? So radius, force, so the torque is going to inside. The example you guys had in the lab, what was the lab? Do you remember the lab? I had here a ruler, right? With, let's say, point here, and then here I have some weight, M1, and here I have another weight, M2, right?
Yeah.
Why is that? Why is in equilibrium? Why is in balance? Because if I don't have this here, the torque is going to cause this ruler to rotate, right? It's going to be unbalanced, right? The fact that it's balanced, that means the sum the sum of all torques is equal to 0. The torque that this one here, this is R1, this here is R2, right? R1 times the force of gravity, right? M1G, right? M1G, that's the, and M2G. Are two forces, one force going this way, F1, and this is F2. Now, F1 is going this way. It's a torque, it's causing a torque to go there. That's torque 1, and that is going this way, right? There is a vector that is the product of R1 times M1G. Now, this side here is causing another torque. Now, R1 is this way, going this way to the force, right? And the torque is going out, and that is torque 2, and it's going out. So those two torques are canceling each other. And that's why we have this here in equilibrium, balance, okay? Right? This was the last experiment that you guys did.
I don't get the pointing inside and outside thing. I don't get that.
You don't get that?
No.
Okay.
I mean, I get what you're doing. I understand.
I see.
it, but
This is
I don't
R1,
see why.
and this here is F1,
Yeah.
right? So you have R1. Let me erase this. So F1 is here, right? I can translate F1 here, because what's here, I can just move here, right? So R1 is here, I'm pointing this way, goes to F1. So my thumb is going inside.
No, I get that. I like what does it do in real life? Like, what's the? I don't get it. I don't get why you're doing that.
So I'm assuming, like, say you use the example of the door. So like, when you're opening the door, you have like one direction, right?
Right.
But as soon as that direction kind of deflects because of the hinges of the door. So like, if you didn't have the hinges, you would just keep going straight, right?
Yeah.
And
It's-
but because you had hinges on the door, like the direction is over there, right?
So the
So you can't-
hinges,
yeah.
yeah, the hinges is holding that position there, right? So when I apply a force here at the door, move it that way, so the door moves, rotates,
Yeah.
right? Have the axis, right? It's like this is the axis point here, right? I apply a force here, it's gonna rotate in one direction. So you need to have a way to represent that. And torque is a way to represent that. Now, if there is, the same way it goes this way, it can go the opposite way, right? So we need a way to represent that too, and cannot be, the torque cannot be in the same direction, right? Because, you see, how can I explain this equilibrium here? That the two values have to cancel each other, okay? So if this mass here is 2 times M2, or M2 is 2 times M1, R1 needs to be half that value, right? Because the product is going to be the same. The magnitude of the torque is going to be the same. But they need to cancel each other. So how can I explain that? Well, they have to have opposite directions.
So the inside-outside pointing thumb is just to say that they're like.
I think it's because
Opposite.
you're thinking of it in 2 dimensions, as it's just going left and right.
Right.
But when it's in equilibrium, it's in balance from left and right, but also like front and backwards. So if it's this way, it has to also be the same in the other direction, right?
It is, the vector is a mathematical model to explain things, okay? And works, right? It works, all right? So, you know, this is just another model, right? It's abstract because it is a model, right? It's abstract. That's why it's kind of sometimes difficult, right? It was very difficult for me too to learn these things, right? But you know, with time, with understanding.
I understand the physics part of it. I just didn't understand why we were doing that. What we're No, but not get it, just show that it's opposite direction.
Opposite direction, yeah. It's a convention, right? That if this way it goes that way, but if the other way has to be opposite, so it cancels each other. So satisfy the describing this. Okay. What was the other vectorial product that we discussed last time? You know, another example. I talk about torque. What else I talk?
Momentum.
Angular momentum, right? So the angular momentum was also a vectorial product. This L was R P, right? R P. P is the linear momentum, right? So if I have a mass here somewhere, has velocity, it has also linear momentum, and if I have a reference point here, this point K, and this is R, so the angular, right, the angular momentum here is going to be this product, right? Now remember the example that I had with that bicycle wheel, right? No. So the same like linear momentum is conserved, right? The only way to alter that is by what?
Changing direction.
How can I change linear momentum? P is equal mv, right?
Yeah.
If there is a change in linear momentum, like a delta P, mass is constant,
Yeah.
it's not going to change, so I have a change in velocity, right? So the rate of change, in order to change this, I have a rate of change here too, so this here becomes what?
Acceleration.
Acceleration. M times acceleration is force. So I need a force to be able to change linear momentum, otherwise it's going to be conserved. That's Newton's first law. Remember that, I have a body moving at a certain velocity, it's not going to change until a force is applied, or at rest. Now here, with the angular momentum, the analogy is the same. If I have a delta L, right, over time is going to be a delta P over time here. But this here is force, right? We know this is force, so now in order to change the angular momentum, I need to apply R times force, a torque. So the torque is the analogy here that for linear momentum, we had the force. For angular momentum, we need to apply the torque. The example that I gave with the wheel rotating was because I was holding, right, one side of the wheel and was causing a torque with the weight of the wheel. So the angular momentum is like here, pointing there. I apply a torque, right? Torque going this way. Look, the torque is going this way, R, and this way, so it's going to move the other way, right? You guys see, it's hard to change. The only way to change is by applying a torque. Right? And if you change, the angular momentum is going to be able to change. Okay? So, so from here, we have the L is R, M, V. You guys remember that, right? The angular momentum is R, the radius, M times V. But V, in terms of angular, if this is rotating, right, we have a angular speed, right? What is that, the angular speed? V is equal to what? The angular speed, R, right? You guys remember that?
Yeah.
So I showed that this is equal to that one, right? So when I place that here, I'm going to have m r squared omega,
Yeah.
right? So this here is what we call the moment of inertia, is I. moment of inertia, W. Okay?
So is I M all square?
I,
Is M all square?
yeah, is mr squared, right? And this is for m is here. This is m, so this is a little ball, right? And I have, let's say, a string is moving around, right? The same string. And remember, I gave an example of a circular motion, like, for instance, the Earth or the moon going around the Earth, right? And I also gave the example of a projectile motion, right? And let's say here, this position here is going with this velocity. I have this angle here, and I have, this is the displacement. And I showed that here, in this case, the radius is not changing, right? It's going around. So here, the angular momentum is conserved, right? And here is changing, right? So this angular momentum is equivalent to mass, right? It's equivalent to mass, right? As like here, for instance, you see mass times the velocity, right? Now, and this is linear momentum. Linear momentum is mass times velocity. Angular momentum is moment of inertia times the angular velocity. Now, this moment of inertia, if it's just a piece of mass like hanging with a string, you just calculate the radius times the mass, right? Now, if it's a solid, the moment of inertia is going to have a different formula, and you're going to have to use calculus to calculate that, right? So let me just move the camera here to show those formulas that I'm talking about. So for different bodies that have different shape, the moment of inertia, this is all in tables, right? You guys don't need to memorize that. But for instance, the Earth or the Moon is spinning, right? Just the fact that it is spinning by itself, it has a moment of inertia. And if you want to calculate the moment of inertia, you're going to have to put the mass of the Moon here, right? And the radius of the diameter divided by 2, and 2/5. That's it. That's the moment of inertia. If you want to calculate moment of inertia in relation to Earth, on the center, that the Moon is rotating, you're going to have to add also, you know, the distance from the Earth to the Moon, and you're going to have to add to this to calculate the total moment of inertia. Is that okay?
You said divide r squared by 2.
What is it?
But you said it's 2/5.
Oh, 2/5 mr squared.
Okay, but you said divide by 2. I heard, unless I heard you
Divided
wrong.
by 2. No, I said that this would be the moment of inertia of its rotating on its own axis,
Okay.
right? Because the Moon is rotating too, right? So the Earth is rotating, right, on the
Okay.
axis. But also is going around the Sun,
Right.
rotating and going around the Sun. So then you need to add that one too. And you see, this here is like a bar, right, with a cylinder. If I'm rotating here, right in the center, the formula is 1/12 ml squared. But if the axis is on the side, the moment of inertia is gonna be a different formula. Okay? If you have a ruler and you try to rotate from the center of the ruler, you're gonna have to apply, a certain rotation, right? But if you wanna try to rotate from the extreme, it's gonna be different, right?
So it's
So-
different from it.
So it's like a different
It's
resistance.
still perpendicular, right?
You're perpendicular, yeah.
So it's like if you're trying to spin a basketball on your finger
Yeah.
versus like attaching the basketball to a string. And
Oh, yeah, it's gonna be completely different, right?
so is that what you were saying the other last class, that the closer you get to the center, the faster he goes? right?
Yeah, well, that's, you're talking about the linear velocity, right? On a circular motion, right? If you go extend the radius, right? This velocity on this point is less than this one here. That's, the tangential velocity, linear velocity here, going around a disk. If you're getting closer and closer to the center, this linear velocity is reducing. The angular velocity is the same.
Oh, okay.
Angular velocity is the same because the angular velocity is related to the angle, right? How fast that angle is changing. But the linear is covering this distance versus this distance at the same time. So if I'm covering different distances at the same time, so they have different velocities. Right?
Yeah.
So my question to you, we kind of cover almost everything so far. My question to you, can you next class do this presentation, trying to cover, and you don't need to do, one student. You can kind of complement each other, right? So somebody can talk about one part of it, and the other ones talk about a different part, and so on. So that's going to be the task
Are we
for
gonna go
next
over
class.
all those formulas?
No, you don't need to go over. This is, I just put here so you guys understand that the values are different. And whenever, if you need to solve a problem, usually the problem even gives you the formula. You're not expected to memorize this, okay?